welcome to the Deep Dive, your essential shortcut to understanding the forces shaping our world. Every digital interaction you have, from AI assistants boosting your productivity to, well, the promise of autonomous vehicles, it all relies on this massive, unseen, and frankly, rapidly expanding infrastructure data centers. So today, we're taking a deep dive into how these critical digital nerve centers are scaling up. Our goal, give you a really clear understanding of the monumental shifts happening in data center infrastructure, specifically how they're trying to get bigger, faster, and cheaper through smarter designs. We've pulled insights from McKinsey's private capital practice, their August 2025 article, and a stack of other research that really paints the picture. Get ready to connect some maybe surprising dots. Okay, let's unpack this. And some of these numbers are truly eye-opening. The sheer scale of capital needed just to build this infrastructure. It's immense. Global spending on data center infrastructure. And remember, this isn't even the IT hardware itself. It's projected to blast past $1.7 trillion by 2030. Yeah, that number alone, it just underscores the huge commitment needed just to keep our digital world humming.
It absolutely does.
Yeah.
And, connecting this to the bigger picture, it's not some random surge, right? This unprecedented demand, it's really driven by three powerful forces.
Mm-hmm.
The explosive expansion of AI, the proliferation of edge computing, and these big advancements in high-performance computing, HPC.
Right.
This isn't just about, smoother streaming for your favorite shows. This is the foundational backbone for almost every new digital technology that's emerging today.
And all that computing power naturally needs a tremendous amount of actual power.
Yeah.
The energy side is just as staggering. Data center power demand projected to hit 1,400 terawatt hours by 2030.
That's huge.
It is. It's equivalent to a significant 4% of total global power demand. And just to put that in perspective for, say, the U.S., the United States alone needs to more than triple its annual power capacity just for data centers, going from 25 gigawatts in 2024 up to over 80 gigawatts by 2030.
80 gigawatts.
Yeah.
Just in the U.S.
Just in the U.S. worldwide, we're looking at maybe 220 gigawatts by 2030. So if that's the energy demand, what are the real world implications for our existing power grids? How are developers even starting to tackle that?
Well, what's fascinating here is how that translates directly into physical scale.
Yeah.
And the strain on existing infrastructure. We're talking about data center campuses that are no longer just, tens of megawatts.
Right.
We're seeing them expand to hundreds of megawatts, even a gigawatt or more. I mean, these are massive facilities. They're designed on plots of land bigger than 4 million square feet.
4 million square feet.
Yeah. Meta has publicly announced plans for a 2-gigawatt campus in Louisiana.
Yeah.
So this isn't just an incremental increase in size. It's a fundamental shift in how we conceive, design, and build these critical structures. And it puts immense pressure on those traditional grids.
Which brings us to a really critical point. Despite this explosive growth, this incredible demand, the way we've actually been designing and building these digital behemoths, well, it hasn't always kept pace. Simply trying to scale up the old methods just leads to huge inefficiencies in cost and speed, everything.
It's a fundamental challenge, yeah. Consider a vivid example. If you tried to build a 1-gigawatt data center using the traditional approach, setting up multiple repeatable centers, each with its own independent redundancy system, you'd quickly hit a wall. Given that current diesel generators are typically, 3.5 to 4.0 megawatts per unit, a single 1-gigawatt data center would need up to 290 generators.
290?
Yeah. I mean, just imagining the sheer number of oil changes for that many generators gives me a headache. It really shows how impossible the old way is becoming. It underscores the need for a complete rethink of the design methodology.
That generator nightmare is just one symptom, isn't it? Companies are actually grappling with 4 huge challenges right now. The first, and maybe the most fundamental, is just securing adequate power.
Right.
Traditional power grids often just don't have the capacity for these massive facilities without, extensive time-consuming upgrades. So this has developers looking at alternative solutions, things like behind-the-meter natural gas turbines, or even, nascent tech like small modular reactors, SMRs.
Which have their own hurdles.
Exactly. As you can imagine, these come with their own regulatory headaches and really long lead times. It's not a quick fix. And it's not just about getting power to the data centers, it's what happens inside. These new AI servers, they generate incredible heat.
Which brings us neatly to the second major challenge, designing truly efficient and scalable cooling systems. The old air-based cooling is often just not enough anymore. Indeed, the cooling dilemma, that's perhaps one of the most immediate and complex challenges right now. Developers are essentially making these big bets on technologies that are evolving really rapidly.
Yep.
We basically have 3 primary rack-based cooling technologies emerging that kind of illustrate this shift. You've got rear door heat exchangers, or RDHXs. They combine cold air with liquid-cooled heat exchangers, good for maybe 40, 60 kilowatt rack densities. These are probably the most similar to conventional tech.
Right, the closest step.
Yeah. Then there's direct-to-chip technology, DTC. This moves a liquid mixture directly through a cold plate that's in contact with the hottest components, the power-dense ones. This can handle more, like 60, 120 kilowatts. And it's currently the most popular, often because you can retrofit it.
Ah, okay.
And finally, you've got liquid immersion cooling. This is where servers are completely submerged in a dielectric fluid. Think dunk tank for servers. This can handle 100, 150 kilowatts, especially with dual-phase immersion. It's the least common right now, but highly effective.
Wow.
The difficulty is choosing which one to integrate, because these decisions have really long-term implications for the design, the cost, the operational efficiency over the entire lifespan of that data center. It's a big choice.
So just to simplify, we're moving from just blowing air, basically, to actively pulling heat away with liquids right at the chip, and even, like you said, fully submerging the hardware. This isn't just an upgrade. It sounds like a fundamental shift needed for these new, incredibly dense AI workloads.
Precise.
It sounds like making the right cooling bet isn't just about efficiency today, but it's about future-proofing the entire infrastructure for decades. That must be a huge pressure point for these developers.
Absolutely, yeah. The wrong choice now could cripple a facility's future capacity down the line.
Okay, so beyond power and cooling, you need people to actually build these massive facilities. And that brings us to our third major hurdle, a critical shortage of skilled labor. You need thousands of workers on site during peak construction. That severely strains resources, it inflates costs, and it can lead to high turnover, which then impacts safety and quality. It's just a huge bottleneck in the whole process. And the final piece of this really complex puzzle involves the supply chain. While things have maybe improved somewhat since the height of the pandemic, a bit, they haven't really scaled sufficiently to meet this projected demand explosion. Lead times for critical, long-lead equipment like those massive backup generators, the switchgear controlling power flow, the transformers adjusting voltage, they all remain challenging.
Still long ways.
Still long ways. And on top of that, you've got new tariffs and export controls adding volatility. That's leading to a projected 5–10% cost increase on mission-critical gear just for U.S. players. It really is a perfect storm of complexity, driving up both the cost and the build-out time.
Yeah, it makes things tough.
So what does this all mean for building the future? I mean, it sounds pretty bleak, but the good news is there's massive potential for improvement here. McKinsey's analysis suggests that by optimizing design and construction, we could potentially shave 10 to 20% off project delivery time.
That's significant.
And achieve 10 to 20% savings per data center on average. That's not just a big number in isolation. It's a potential reduction of up to $250 billion from that huge $1.7 trillion spend we mentioned by 2030.
$250 billion.
A $250 billion incentive to basically rethink everything we know about building digital infrastructure.
It truly is. And, part of that efficiency gain comes from a relentless focus on minimizing wasted energy. Modern data centers, they're targeting a power utilization efficiency, or PUE, as low as 1.1.
1.1, okay. Compared to what?
Well, compared to current industry averages, which typically hover somewhere between 1.5 to 1.7. So achieving a PUE of 1.1 means you're maximizing your computational output while dramatically minimizing energy consumption and, by extension, your environmental impact. It's really a metric of just how efficient these new designs can potentially be.
Okay, so let's dive into these strategies then. The 6 key areas that could redefine data center design and construction, turning these challenges into, massive opportunities. The first one is leveraging scalable reference designs with sequential phasing.
Right.
So instead of completely custom builds every single time, the goal is for 60 to 80% standardized designs with just 20–40% customization for specific site elements, like maybe the ground conditions or local codes.
Makes sense.
This allows for modularization, for off-site assembly, consolidated procurement, which significantly reduces that supply chain risk we talked about. It really sounds like applying a manufacturing mindset to construction.
Precisely. It's about creating a repeatable, optimized blueprint, not reinventing the wheel every time.
Okay, building on that, the second strategy focuses on an integrated end-to-end delivery model. What does that mean exactly?
It means truly linking site selection, design, and construction with clear accountability from start to finish.
Ah, Okay, not siloed.
Exactly. And using tools like generative scheduling software that can run thousands of iterations to find the absolute optimal plan. This could potentially improve delivery schedules by up to 20%. It's about taking the guesswork out of incredibly complex project management.
Got it. And the third strategy. This one involves rethinking power, mechanical, and electrical at scale, including a review of overall system redundancy.
Yeah, this goes back to those gigawatt scale facilities. For those, simply stacking redundancy layers on top of each other, the traditional way, it actually leads to over-design. It's too much.
Too much redundancy.
In a way, yes. Or rather, inefficient redundancy. The focus needs to shift to an overall campus redundancy design, looking at the whole system. This allows for more nuanced, risk-based decisions to optimize equipment and still achieve high reliability, but without all the unnecessary cost and complexity of just layering everything multiple times.
That does make sense, shifting the risk and complexity view to the campus level. And that same principle of smart modularization, it seems to extend to how these places are actually built. The fourth strategy moves us beyond supplier-specific modular and prefabricated solutions.
Right. Prefab is already used quite a bit, actually. Maybe 40–60% of parts, and the leaders are pushing 80–85%.
Okay.
But the next step is potentially revolutionary. It's about building larger, integrated modules in dedicated fabrication yards off-site and then shipping them to the site, much like the oil and gas industry does with those massive offshore platforms.
Wow, like huge Lego blocks.
Pretty much. This moves a lot of that skilled labor off the potentially chaotic construction site into a controlled environment, which dramatically enhances safety and quality.
Okay, that's huge. And the fifth strategy circles right back to our earlier discussion, integrating scalable technologies and making those big bets on cooling.
Yes. As we discussed, choosing between RDHXs, direct-to-chip, or full liquid immersion cooling, it's a critical long-term decision. It's not just about today's needs. It impacts the entire data center's design, its cost, its operational efficiency over its entire 15, 20-year lifespan. Getting this right is absolutely paramount.
The decision made now really reverberates for decades, defining the capabilities and the cost structure of that facility.
Exactly.
Okay. And finally, the sixth strategy, strategically enter collaborative contracting models.
This sounds simple, but it's important. Bringing contractors and suppliers in early, right from the project's inception, fosters a cooperative environment.
Instead of adversarial.
Exactly. It aligns everyone's interests and lets you leverage their collective expertise much earlier in the design process. It's not just about, good vibes. This approach can lead to tangible 3 to 5% in capital expenditure savings. And it directly addresses those critical pain points, like supply chain unpredictability and the sheer speed of build-out. Feel like a fundamental shift from adversarial contracting to, true partnership.
3 to 5% might not sound huge, but on multi-billion-dollar projects.
It adds up very quickly. Absolutely. Now, what's truly critical to overlay across all these strategies is adopting a lean manufacturing approach.
Okay, tell me more about that.
This isn't just about building faster or cheaper on one project. It's about minimizing waste and maximizing productivity across an entire portfolio of projects, not just individual ones. It's a systemic change in how these massive endeavors are managed from the top down.
Right, thinking programmatically. And this lean mindset, it applies across 3 key systems that impact everything.
That's right. First, the technical system. This means using fit-for-purpose tools like construction simulations and digital twins for better decision-making and operational support. So you can test and optimize the build virtually before you even break ground.
Smart. Okay. Second
is the management system. This means establishing the right performance management offices, both internally, maybe with the owner, and externally with the contractors, to efficiently deploy resources and ensure everyone is accountable for hitting those targets. It's about creating a dedicated structure to actually enforce those efficiencies.
Makes sense. You need the oversight. And third.
And finally, the people system. And this might be the hardest. It's a culture shift towards embracing innovation, breaking down those traditional silos that often plague large, complex projects.
Yeah, the finger pointing.
Exactly. And creating entirely new roles, perhaps, like dedicated blueprinting teams focused on standardization or internal capital expenditure controllers really scrutinizing the costs. It's about a complete transformation of how we think about building really from the ground up with people at its core.
Wow. What an insightful deep dive. It is crystal clear the future of our digital world, especially driven by AI, really hinges on a fundamental transformation of data center construction. We've seen the incredible demand, the immense capital required, and those very real challenges in power, cooling, labor, and supply chains.
Yeah, quite a list.
But crucially, we've also explored these innovative design and construction strategies that promise to deliver these essential facilities bigger, faster, and cheaper, potentially saving billions, as you said, while dramatically speeding up our digital future.
What's really fascinating here, I think, is how these seemingly niche details, talking about PUE or modular construction, how they directly translate into the reliability, the speed, and ultimately the cost of every single digital service you use, from your online meetings to the latest AI assistant you're playing with. And this raises an important question, really.
Okay, leave us with this. As you scroll through your favorite AI-powered app later today, maybe take a second to consider that invisible infrastructure making it all possible, and the incredible engineering pushing its limits every day. What new innovations do you think will emerge next to further optimize these digital powerhouses? And perhaps just as importantly, what role do you see sustainable design playing in that future?